Hello everyone. Good morning, good afternoon, and good evening. I'm Hardik Maheshwari. Today I'm going to talk about FOLAR, Foggy Latent Representations for Reinforcement Learning with Partial Observability. This is a joint work with my colleague Harshad Khadilkar. We are part of the Planning and Control Research Group under the broad umbrella of TCS Research. We are based out of Mumbai, India. Reinforcement learning algorithms in general have been very successful in sequential decision-making processes. However, their application has been limited by their high sample inefficiency compared to supervised and unsupervised settings. RL algorithms learn by interacting with the environment. Although the way model-free RL algorithms are structured, most of the information contained in the samples collected is thrown away. When applying any off-the-shelf RL algorithm to partially observable environments, where information is neither perfect nor complete, learning is unstable and brittle. In addition, poor knowledge of the environment leads to overfitting over the noise. In literature, there have been works to overcome the above-mentioned challenges and improve learning. One school of thought is to learn better representation by imposing a constraint of reconstructing the entire state or observation from the latent representations, forcing the model to encode all the information into dense representations. However, this creates an additional burden on the model as it has to now learn reconstruction in state space while figuring out the policy to achieve the goal. Model has to encode information that is irrelevant to the task at hand. One of the example is shown in the figure, where if the task is to learn driving, learning to reconstruct cloud or the distant object in the background creates additional challenges for the model. We humans do not care about these things while driving or when learning to drive. Another way to approach this problem is to learn representation prior to policy learning using autoencoders such as VAEs to decouple the policy and learning latent representations. This mitigates the issue of learning reconstruction and policy at once. However, this is not suitable for POMDPs due to noise. There has been recent work in defining a metric over latent representation which can ensure the relationship in the state space is preserved as in latent space. This helps in learning better representations. However, calculating metric, for example, bisimulation similarity in a partially observable environment is unclear and computationally expensive. In reference to better utilization of samples collected, self-imitation learning has provided an interesting way to learn representation while having an imitation learning framework that augments the representations learned parallel to the policy optimization. They sample the experiences of best action taken when the value prediction has the highest error. We considered this as one of the baselines for our experiments. We hypothesized that augmenting latent representation with predictive loss, that is prediction in the latent space, not the reconstruction, and learning end-to-end generates better policy and sample efficiency as opposed to decoupled learning of representation and policy in POMDPs. The key contribution of our work as follows: proposing a training paradigm and loss function to learn robust latent representation in POMDP settings contextualized on latent representation of belief state, and ability to modify any off-the-shelf RL algorithm to improve the sample efficiency and exploration characteristics. These are the notations that we use for defining MDPs and POMDPs. In POMDPs, we have an observation that is a part of the state and is visible to the agent. The state as a whole is not visible to the agent. Figure represents the system architecture that we have used. Let us assume we are at currently time step t. We encode all the observation from t minus k to t using an encoder and generate its dense representation ht minus k to ht. These representations are then fed into RNN, in this case LSTM, to generate a latent representation of the belief state that we call it as ZT. This ZT is then passed on to three different heads: policy, value, and next state predictions. Policy and value networks are very similar to the actor-critic framework. In the prediction network, we predict the hidden representation of the next state, ht plus 1, from ht. While training, we encode the next state from the samples using an encoder to generate a target for the next state prediction network. A quick note on encoders: all the encoders share weights among themselves. During training, we do not allow gradients to propagate directly from prediction loss to the encoder as it creates instability in the training. This approach can be combined with any on-policy off-the-shelf RL algorithms. Generalized policy update in on-policy algorithm is defined by the first equation. Gradients for policy parameterized by theta are proportional to log probability of AT given ST. Capital A of ST AT is an advantage function. H of pi theta represents entropy of policy and beta parameter is a coefficient and hyperparameter. Higher values of beta are used to encourage more explorations. We augment gradient update with gradients from loss function LT and L, which is mean square loss between predicted HT plus 1, which is an output of prediction network, and encoded HT plus 1. Let us consider proximal policy gradient algorithm. Loss function can be augmented as shown here. Please note we also clip the next state prediction loss similar to clip loss in PPO to keep lower bound in policy updates and not let prediction loss overwhelm policy and value loss. We test our algorithm over two mini-grid environments with different characteristics and two sets of grid size. The first environment is dynamic obstacles, which has random obstacles moving around. The goal is to reach a green tile while avoiding all the obstacles. Touching any obstacles would end up in termination of episode and reward as -1. We test it over two grid size 6x6 and 16x16. The second environment from mini-grid library is door key, where an agent has to first pick up the key, open the door, and then reach the green tile. This is an hard exploration task as a corridor or the passage provides a bottleneck in exploration. We consider two grid size of 6x6 and 8x8. For both of these environments, there are 7 discrete actions. Reward for reaching the goal state is proportional to the time it took to reach the goal. Episode terminates after a fixed number of time steps, which is a function of grid size. The visible grid size as shown in the figure is 7x7, while the agent being in the bottom center. Input here is structured input of matrix and not the RGB pixels. We also wanted to test our algorithm over a fully observable environment with input as RGB pixels. We have chosen a catcher environment where the objective is to catch as many tiles as possible. Grid size for this has been chosen as 32x32. All the experiments reported in this presentation are done with PPO. However, we have performed one set of experiments with A2C, which is reported in the paper, and it shows similar trend. Lower grid size environments are done over 10 random seeds, while higher grid size is done over 5 random seeds for statistical significance. The shaded region in the following plots denote 95 percentile confidence intervals. The left graph shows the training results for dynamic obstacles with grid size 6x6 and entropy coefficient beta constant at 0.01. We can clearly observe that eta is equal to 0.1 outperforms both baselines, not just in expected rewards, but also in the rate of convergence. In addition, we can conclude that apart from eta is equal to 10, which is an extreme value, all other values perform better than the baselines. In the right plot, we change the beta parameter, which is now exponentially decaying to 0.01 from 0.2. We can see that the change leads to convergence in almost all the algorithms, and the results suggest that having a higher entropy coefficient allows for better exploration even in vanilla PPO, reducing the impact of neta for this relatively simple case. However, neta is equal to 0.1 and 0.5 slightly outperformed other algorithms. This is training results with 16x16 grid size in dynamic obstacles. Similar to 6x6, we can see a trend of neta is equal to 0.1 performing best, followed by neta is equal to 0.5 and 1. However, we see a marked difference when the beta is exponentially decayed. Plots corresponding to neta is equal to 0.1, 0.5 and 1 are much better as compared to baselines. This is a highly dynamic environment, and having a higher weight to predictive loss leads to degradation in performance. The probable cause is that the agent prefers to remain in one place, which has more predictable observations. Now moving on to Dörke environment, we first start with grid size 6x6. There is not much difference in convergence values across algorithms when beta is constant at 0.01. Dörke environment is comparatively easier to solve, which can be observed as all the algorithms converge fairly quickly in 3000 episodes as compared to dynamic obstacles of the same grid size which required 60,000 episodes. When beta is exponentially decayed as shown in right graph, performance for neta is equal to 10, vanilla and SIL degrades. Polar with any value apart from neta is equal to 10 is unaffected. On the other hand, there is a remarkable difference in results for 8x8 environment. We can see that only Polar with neta is equal to 0.1 and 1 are able to solve this hard exploration task when beta is constant. The same trend is visible in beta when beta is exponentially decayed, with the exception of neta is equal to 0.5 reaching the same performance as 0.1. We note that 8x8 Dörke is typically not solvable from scratch by vanilla RL algorithms. Lastly, this plot showed training graphs over catcher environment. We have normalized rewards for plots here. The variance for the low entropy training case is very large, although SIL and Polar seem to be doing better than vanilla PPO. The exponential decay beta case indicates that Polar with the higher values of neta performs well, whereas vanilla and neta is equal to 0.1 converge to suboptimal values. SIL seems to be doing approximately as good as other Polar curves with minor edge to Polar. However, we do note that the variance across various random seeds is too high. Interesting trend to note here is that neta is equal to 10 is either performing better or as good as other curves. The three environments that we have just presented in decreasing order of their dynamic nature, we can see that higher values of eta are favorable in the static environment. Performance degradation is observed when the eta is high in dynamic environment. We have provided a detailed discussion over the role of eta in the paper. One of the ablation studies, we ran a set of experiments with 10 random seeds and trained over different values of eta. We can see that there is an initial jump and then the performance degrades. These experiments are conducted over 6x6 dynamic obstacle environment, where neta is equal to 0.1 provides the best performance as seen earlier. We also wanted to test our learnt models over its generalization capabilities. We ran our learnt models over unseen environments to understand if the prediction loss helps in generalization. We ran the best performing model of Polar, trained over 16x16 dynamic obstacles, over an empty room environment where there are no obstacles and it just needs to reach the goal state. We can clearly see that Polar outperforms in both cases, that is beta is equal to constant and exponentially decaying. It is worthwhile to note here that when beta is equal to 0.01, only Polar is able to successfully solve all the grid sizes while all other algorithms have failed. Exponential decay of beta helps in exploration and hence the SIL improves. However, Polar is still outperforming it. This provides empirical evidence that using the prediction of the next state improves the understanding of the environment for the RL agent. To summarize, I presented Polar, a method to learn robust latent representation in partially observable environments, loss function of prediction network which can be augmented with any on-policy off-the-shelf algorithm to improve its exploration and convergence characteristics. The hyperparameter neta controls the magnitude of prediction loss and can be tuned based on the predictability of the environment, but most reasonable values result in superior performance compared to baselines. Polar performs especially well in hard exploration tasks and larger grid sizes, where entropy coefficient is kept static, indicating improved latent representation that leads to more focused exploration. In future work, it would be interesting to look at adaptive neta, which could learn better policy even faster. Thank you for tuning into this talk. Here are the contact details. Do share our feedback and questions. Stay safe.